I've sent you the link to sort of revision questions. The topic of the test will be basically whatever we have done so far, which is molarity, making up solutions. I'm not going to ask any questions about health and safety, because that's, we don't want that. We don't need that at that point. You are all familiar with working safely in the lab. So molarity, converting grams to moles and the other way around, making up solutions, potentially pH, buffers, strong acid, weak acid, maybe. And spectrophotometry, you need to be aware, you need to be able to apply the Beer-Lambert law, maybe. And then data analysis, so mean, median, mode, sample, standard deviation, sample, variance, population standard deviation, population variance. You need to know maybe what is interquartile range. You need to know maybe what is the margin of error, what is a lower bound, what is an upper bound. You need to know what kind of hypothesis testing you need to apply. So remember, t-test is two samples comparing with each other. Chi-square goodness of fit test is you compare one data set with expected data and check whether these fit. You need to know what a p-value is. You need to understand what a p-value tells you, maybe. You need to be able to interpret a regression coefficient, this R, maybe. So, these are the things that I would expect. If you can do that, there's no reason why you shouldn't get 100% in a test. Have you received 100% in a test here so far? Anyone? Yeah? Wow, that's cool. Bless you. The rest, obviously, 100% would be something to aspire to. So definitely, I want to give you 100%. So what I'm going to do in this session is just simply, I'm not going to calculate through all these things, because you've got the model, you've got the correct answer here at the end of each of these questions. And I think I've sent you the link to that, haven't I? To these revision questions, yeah? So you can check out what it is, how it works, etc. I just want to quickly go for each of these questions through the strategy, what you need to apply in order to solve this question. Does that make sense? Yeah? So for the first question, you have a stock solution of 0.5 grams per mole, and you want to have a working solution. Very clearly, stock, working, it should trigger in your brain the response, I need to do C1 V1 equals C2 V2, right? Or if you think about the doctor and the pharmacist, the doctor says, I want this times this, and the pharmacist behind the desk says, oh, we only have that. It's exactly the same thing. So for the first question, you would need to apply this C1 V1 equals C2 V2. And the little sort of devil in the detail is you have different units. So here you've got gram per milliliter. Here you've got milligram per milliliter. you have to be aware of that, and you have to say, okay, milli just means 10 to the minus 3 when you do that. So don't neglect the conversion of the units. Okay? Happy with that? Wonderful. For the second question, you need to make 250 milliliter of a 2 millimolar solution. Your substance has a molecular mass of 180 gram. I might even write that on a different page. Just 250, 2 millimolar, and 180. Echt. Can't see it properly. Yeah. 250 milliliter, 2 millimolar solution, and you have 180 grams per mole, and you want to know how much you have to weigh in. What is the strategy here? What would you do? How would you solve that? Sorry? Yeah, or just simply say what your strategy would be. What of the techniques that I showed you? Dimensional analysis. That is the easiest way. So dimensional analysis. Okay, I better write analysis before people get the wrong idea. And this is, you are guided by the units. You are looking for the unit grams, so 180 grams per mole. Grams is what we want. Mole, we don't want that. So we find something else that has the unit mole in it. So that would be 2 times 10 to the minus 3 mole per liter. And the moles cancel out, so that's good. We are looking for something with liters in it, and that is 250 times 10 to the minus 3 liters. And now the liters cancel out. And basically that is how the dimensional analysis guides you through your equation. Okay? Does that make sense? Say yes. Okay, so next question is pretty much the same. You want to make up 350 milliliter of a 12.5 millimolar. Your stock Okay. It's not the same, sorry. You want to make up 350 milliliters, 12.5 millimolar working solution. And here is this again, working solution, stock solution. What is the technique? Loud? C1, V1. So here again, for this one, you have C1, V1. Working, stock, C1, V1. Yeah? As simple as. Okay, next question. You have a 1% weight per volume stock solution. So what's the strategy? C1, V1, exactly. Yeah. You have a 1% weight per volume, and you want to make 10 milligram per liter. Now here is, again, a little devil in it, because you need to convert the 1%, this guy here, you need to convert that into something useful here, like 10 milligram per liter. Yeah? And for that, you obviously need to know What does this 1% actually mean? What does it mean? Exactly, it means 1 gram per 100 milliliters. Yeah. And you can, of course, play with that a little bit. You just simply multiply it by 10, and you get it in liters. So this is the same as 10 grams per 1,000 milliliter. Yeah, is that right? Or 1 liter. So you've got 10 grams per liter into 10 milligrams per liter. And again, you can very easily convert that, bearing in mind that you have grams and milligrams. C1, V1. Okay? Happy with that? Now, here we've got something about the absorbance of a solution is 0.1. Path length is 1 centimeter. Extinction coefficient is 2,000 liter per mole in centimeter. What's the what's the technique that you would need to use for that? Beer-Lambert law, which is absorbance, absolutely right. Absorbance equals extinction times concentration times the path length. You are looking for the concentration here, so you shove everything else to the other side, and you have absorbance divided by extinction coefficient, bless you, by the path length, and you very easily get your concentration from that. Yeah? So another very simple strategy and technique, very easy. You don't even really have to think about this in terrible detail. All you need to know is the Beer-Lambert law, which, of course, you have used before, and you shouldn't have any problems with that. Bless you. Jesus, what's going on here? I told you that the best remedy against persistent cough is a strong laxative. But it works also when you sneeze a lot. Yeah, that's might be useful. Okay, so this one here, this question here, the absorbance of a solution is 0.22, path length, extinction coefficient, what's the concentration? Again, the same thing, not even in a different color. It is the Beer-Lambert law. Absorbance equals absorbance coefficient times concentration times path length. Okay, so next one, pH. Well, I haven't put in a lot of pH questions, have I? Huh? In this revision session, in this revision sheet. Maybe it tells you something. Maybe, I don't know. Okay, so what is the pH of 125 milliliter solution of 0.5 molar sodium hydroxide? What would you need to know for that? Let me just write this on another page. What is it? 0.5 molar sodium hydroxide, pH we are looking for, and I said it's 125 milliliter. Right. Now, sometimes you probably find that information, that I do a little bit of overkill in terms of information. This case is a typical one where there's overkill. What is the thing that we don't need? The volume. We don't need the volume. It doesn't matter for the pH whether we have 125 milliliter, 1 nanoliter, or 168,000 liters. The pH is always the same. It's volume independent. Yeah? Happy with that? So all we need to know here is, or what we need to know really is an equation where we can calculate the, and in this case, we don't have protons, we have OH minus because we have NaOH, and I would expect you to know that this is something that produces OH minus. So we need to find out what the POH is. And the POH in this case, how do we calculate that? Negative log of 0.5. Yeah? But you are not asked to do the POH. We ask for the pH. So in this case, pH equals absolutely right, 14 minus the POH. Yeah? Excellent. So always check out what am I actually asking for. Is it pH or is it POH? Make sense? Fantastic. God, I'm good. Okay. So that's this one here. Let's do this one here next, because a lot of people have asked me since they stumbled into that in the quizzes. So what is the POH of a 0.1 nanomolar hydrochloric acid solution? What is it? 7. Why is it 7? Or close to 7? Why? Absolutely perfect. I couldn't have said it myself any better. The concentration of the hydrochloric acid is very, very, very low. And in this case, you have to take into consideration the concentration of the protons in water. Yeah? So usually you would have to say the pH of something is always the negative log of your acid concentration plus the 1 times 10 to the minus 7 molar proton concentration. Because that is the stuff from the water. Yeah? Usually, if the acid concentration is sufficiently high, we can really ignore this part here with the protons. But if the acid concentration is really low, then these 1 times 10 to the minus 7 molar for the protons kick in. So if you have a very, very, very low acid concentration, then the pH is very close to 7. Likewise, if you've been asked what is the POH of such a solution, what would you say then? What's the POH of normal water? 7, exactly. Yeah? It's also 7, or if you like, pOH in this case is 14 minus the pH that you have. Yeah? So if you've got very, very low concentrations, it is 7. Don't forget that. Okay? Happy with that? Good. Now we wanted to say the side chain of an amino acid has a pKa of 6.2. How much of this side chain is in the protonated form at pH 7.2? So what would be your strategy here? What would be the technique? What would be the equation that you use here? You have a pH, you have a pKa, and you ask how much is in the protonated form. Which of the several equations that we've dealt with would spring to mind in this case? Loud? Weak acid? Yes. We are asking for a protonated form, so that implies that there's also an unprotonated form. So the protonated form would be an acid. The unprotonated form would be the base. Can you remember an equation where you have pH, pKa, acid, and base? Can you remember an equation for that? That's good. pH equals pKa minus log of the protonated form, which is the acid, to the unprotonated. And what's the name of this equation? Loud? It's the Henderson-Hasselbalch equation. Yeah? So you've got an HH, Henderson-Hasselbalch, which is slightly different to the MM equation. What's the MM equation? Excellent. I once worked with a colleague who no longer is with us, a very, very top, high scientist colleague. And he said to me, I really never managed to understand how you can calculate a buffer using the Michaelis-Menten equation. And obviously, I was too junior at that point to say, well, nor do I, because that's the wrong equation. Yeah. So what you have here, Henderson-Hasselbalch. So whenever you have pH, pKa, protonated and unprotonated, you want to go for this equation. You can also write it in the different form where you have plus log of unprotonated to protonated form. It's exactly same difference. Okay? Somebody mentioned earlier a weak acid. And the weak acid would kick in if you are basically asked for what is the pH of a weak acid. How do you know that something is a weak acid? It dissociates partially. How would you know that it dissociates partially? In a test? You get a pK. Exactly. Yeah? So if you get a pKa, you would usually assume that this is a weak acid. And if nothing is mentioned about protonated or unprotonated forms, yeah, you would go for the equation for a weak acid, which is pH equals one half of pKa minus log acid concentration. And this always has to be in molar. Okay? Happy with that? Excellent. You can do it if you B&Q it. And I'm a victim of advertising. Okay, now we are here. The mean of the data set, I have to say I take it for granted that you can do that. You just sum them up and divide by the number. Even my son in year 8 is able to do that, so I'm not going to dwell on that. I'm pretty sure you can do that as well. The sample standard deviation, again, I would assume that you know how to calculate that. So what you do is you just simply take the different data points, xi minus the mean, you square it, you take the sum, of that, so you add them all up, and for the sample standard deviation, and for the sample, let's do the sample variance first. You divide by what? N minus 1. Exactly. Yeah? So it's divided by N minus 1. If you have the population, the population variance, you divide by N. And if you want to do the standard deviation, what do? You square root this. Yeah? And again, I would assume that you know the equations for that. And you know how to do it. Okay? Oops. So we have done this one, we have done this one. Interquartile range. Can you remember how this is done? For the interquartile range, you have to find first the mean. No. What do you have to find? Loud? Q3, Q1, and in particular Q2, which is the median. So let's say we have, I can't remember the numbers, 1, 2, 3, 4, 5, 6, 7. So what you do is you just simply order your numbers in ascending or descending order. It doesn't make any difference. And in this case, you just, an easy way of doing that is like that. And you find the middle number. So in this case, this is number 4. Yeah? That's the median, or Q2. And then you find, for the rest, you find, again, for these numbers here, you find the median of these three numbers. And again, here the median is this one and this one here of these three numbers. Okay? And the interquartile range, IQR, is simply this distance here. So that is 6 minus 2 equals 4. So that would be the interquartile range. Okay? Pretty straightforward, I would say. As long as you can sort the numbers in ascending or descending order, you should be able to deal with that. Okay, that's that one. Now you want to analyze data at 95% confidence level. Your significance level, alpha, therefore, is... So the way you deal with that is you say alpha, the significance level, is equal to 1 minus confidence level. And in this case, it would be 1 minus 95% equals 0.05. Make sense? It's pretty straightforward. Again, that is basically here the equation that you need to know for that. You get a p-value of 0.65. And so p-value is 0.65. Alpha should be 0.05. What does that indicate? What does it mean? Remember, if P is high, what happens? If P is high, H naught, cloud, can stay. This means P is larger than alpha, and we say the null hypothesis is not rejected. H null is not rejected. Okay? If P is low, H naught must go. In this case, P is smaller than alpha, and therefore H naught is rejected. We do not accept the null hypothesis. And the null hypothesis is always there is no difference between the means. Okay? H1 is there is a difference between the means. Any questions about that? Great. So that's this one here. The margin of error of a sample with mean 62.2 is 3.2. Now, in one of the, I think it was one of the live streams, but we have done that also in the lecture. Margin of error is basically the range in which we think, in which we are comfortable that our true mean is located. So if we've got a mean of, what was it, 60, 67.2. So 67.2. The mean of, and the margin of error is 3.2. We can express our result as mean plus minus, or no, I should probably say 67.2 plus minus 3.2. So it would be the mean plus minus the margin of error. So in this case, it would be somewhere between 64, and that is the lower bound, to 70.4, and that is the upper bound. Is the mean bang in the middle here? Yes or yes? Yes? Has to be bang in the middle, because on one hand, I subtract the margin of error, and on the other hand, I add the margin of error. So it must be absolutely symmetrical. Okay? Make sense? Perfect. What is the most appropriate test to compare two samples with each other? I said that already at the beginning. If you have two samples that you want to compare with each other, the best test for that is, as far as we are concerned, is a t-test. If the samples depend on each other, if you can do before the treatment and after the treatment, then it is a paired t-test, because you always pair two samples. So before the haircut and after the haircut. And you do that with samples. So before I go to the hairdresser and after I came from the hairdresser, before Rania goes to the hairdresser and after she comes out of the hairdresser, you compare always, in a way, the same person. This is paired. If the two samples are independent from each other, it is an unpaired or independent t-test. They vary slightly in the execution. Oops. There's something missing. And it also depends a little bit if the two samples have the same, if it is an unpaired test, does it have the same variance, same or unequal variance, and also whether you want to do a one-tailed test, one or two-tailed test. two-tailed test. And this one-tailed or two-tailed test depends on your alternative hypothesis. For a two-tailed test, you just simply say that the samples are different. Or I should say sample means are different. Well, let's forget the samples. The means are different. It doesn't say that the mean for the sample 1 is larger than the other. So I would always go for a two-tailed test unless there is a real specific need to do a one-tailed test. Always go for the means are different. The mathematical way you would write a null hypothesis would be, for the null hypothesis, mu1, which is the population mean, is the same as mu2. That's your null hypothesis. Or for the alternative hypothesis, h1, mu1 is not the same as mu2. That's the mathematical way of writing it. Okay? Happy with that? So that is when you have two samples that you want to compare with each other. That's a t-test. If you want to compare one sample which you observe with an expectation with expected numbers, you would go for chi-squared. And in this case, a variation of the chi-squared, it would be, what? I heard something? Goodness of fit. How good, actually, does the observation fit with the expectation? Goodness of fit test. Okay? Happy with that? Can you do the test? It's not getting much more difficult than that. And I want to apologize in advance. Some people might think it is an insult to their intelligence, the test. Sorry. But, when you do this test or any other test, I want you to really write down what you're doing. Show all your calculations. I am a religious person. I believe in divine inspiration. But if suddenly, there is question A, 55 milligrams. Where do these 55 milligrams come from? Did they just drop from the sky? Or did you just, guessed it? Or did the person sitting next to you told you that? So if I don't see how you did the calculation, I can't give you any marks for it, even if the rest is right, even if the number is right. And also, don't forget units. Go back to the little quizzes, try to do them, see if you can do them. If you can, you should not have any problem whatsoever. Okay? Have a good weekend. And if there are problems, email me or Facebook me or something like that. Have a good weekend. Go in peace.